The definition of a regular surface. So remember what I told you, I think in the first class, every time we define kind of the space we want to study, the first thing we need, the next thing, the immediate next thing is to define what are the transformations among them, because eventually we will study everything up to some kind of equivalence induced by the transformations that we are using. So, of course, we are in the kind of the smooth world. So the basic concept now is what is it? A smooth function, but defined over a surface instead over the domain of Rn as you are used to. Okay, so that's what we have to do now. So, and that's easy. And that's easy, but again, keep in mind, every time you feel something is easy, think of what we are using, why it is easy. Because it will not be easy when we leave the world of Euclidean space. Okay? So from now on, S is a regular surface. And let's say O is an open set of R3. An open subset of R3. Okay? So, in fact, the first definition is the most delicate one. So what does it mean for a function with domain a surface, but values, let's say, Rk, we don't care, I mean, a Euclidean space of any dimension, to be smooth. So f from S to Rk is smooth, is differentiable, and again, you can replace C1, C2, C3, whatever you want, if for any local chart so now what does it mean that we have a local chart? Remember, always remember the picture, okay? So we have S, and around some point, now in this moment P is not important, but we have a P and we have a map from some domain of R2, so this is U, this is X, and this will go into an open set of the surface, okay? Surjectively, with injective differential, homeomorphism, and so on. So that's a local chart. So once we have this, and now what we are saying is that now we also have an F into some Euclidean space, okay? So it's pretty obvious what we have to do. In order to go back to old definitions, we can compose F actually with X inverse. So we can go this way to get essentially the same map locally. And now, so if for any F composed X, now F composed X goes from where to where? Goes from mu to Rk. But then it's an old-fashioned map from a domain of R2 to wherever. Okay, so we know perfectly well what it means to be smooth or C1 or C2. Okay. I will comment on this definition a bit later. Now let me list all possibilities. So this takes care of the problem of what does it mean for a function defined over a surface to be smooth. What about a function with now an old-fashioned domain, because now this is, for example, it's a ball of R3, with values on a surface to be smooth? Well, this is easier, because forget that the values are in S. F is actually a function from a domain of Rk, actually even here I could have put any dimensional domain, but this takes values into R3 in particular. S is a subset of R3. If the same F, now thought as from O to R3, is smooth. Okay, so this is just forgetting the fact that you know that the image is inside a specific subset of R3. Well, and now composing 1 and 2, of course, we get 3, because if S1, because of course eventually we will have a map from one surface to another surface. Okay? So if S1 is a regular surface, and we take a map, and F now goes from S to S1, so now this is the prototype situation. When we will say that such a map is smooth? Well, combining 1 and 2. Because this is a map with values in R3, so in some sense I will use 2. No? Forget S1 and replace it with R3. But then, so now it's a map from S to R3, so I look at 1. Okay? If, how can I say it? I mean, if F from S to R3 is smooth in the sense of 1. Okay? So now so combining these things, we know what it means for a function between two regular surfaces to be differentiable. Okay? Actually, before making comments, let me first list a few examples and make some observations. Now, so what is the basic idea? And this will be coming back over and over, even in higher dimensional modern differential geometry. The idea is to recognize when a property is a local property of something, or whatever. In this case, it's a map. So we have a map, and we want to understand whether it has some property. In this case, it's being smooth. But this property is local. Okay, being smooth or not, of course, because now you define what does it mean to be smooth near a point. And then you will say it's smooth everywhere if it's smooth near every point. So being smooth is a local property, whether it has first derivative, second derivative, it's something you check looking at the function near a point, not looking globally at this function. But every local property, because of the definition of a regular surface, can be checked by passing into coordinate charts. I mean, the whole definition of surface or manifold, as we will see, is built in a way that you can transfer local properties from your object, from your regular surface, to domains of Rn, of R2 in this case. Okay? So using the chart, that's the trick that plays. So in particular, here, I'm transferring the property of being smooth to the old property of being smooth between charts. I mean, from a chart to another object. Okay? So, in particular, what does it mean? In particular, this implies, so F, so observations. 1. F between S and S1, smooth. So all the theorems, the old theorems of calculus, which depended only on the local fact of being differentiable, will pass automatically to this new concept. So for example, if it's smooth, it's continuous. So again, how do I prove it? Well, there's nothing to prove. Okay? Okay. For example, just to give you a feeling of... and then you can play other observation. As soon as it makes sense, so for example, you can play all algebraic operations among smooth functions as long as they respect domain and codomain. So for example, if I take two functions, two smooth functions between two regular surfaces, of course, for example, I would like to say the sum or the scalar or the product or whatever, I mean, is again a smooth function. Remember, now, take your calculus book. As soon as you have defined what is a smooth function, what did you do? Well, you proved all this algebraic stuff. Okay? So if I take two functions, the two smooth functions, the sum is a smooth function. If I take a real number and the function, lambda times the function is a smooth function. All these things. Will they hold in this new category? Well, yes, as long as they make sense. So for example, does it make sense to ask for, if I have f and g from S to S1, smooth, does f plus g, is f plus g smooth?
Is it going to find?
The problem is that depending on S1, maybe f plus g does not go into S1. Okay? So that's the only thing you have to be careful. As maps into R3, of course, yes. So if I take f and g from S to R3, of course, f plus g, and these are smooth, f plus g is smooth. Then what else can you do? Everything. I mean, for example, you can take, let's see what I listed here. Well, of course, f minus g, but then lambda f, if lambda is a real number, no? I can certainly dilate or contract a map, and it remains smooth. Of course, if this was going into S1, again, maybe lambda f is not in S1. But for example, what else can I do? I can take the scalar product. At every point, these are vectors, I can take the scalar product. Okay? Now again, this is particularly striking because, of course, if I take two functions with values in R3, the scalar product is a real valued function. So, of course, it doesn't even make sense to ask whether this lies in S1 or not. This is a real number. But anything, now, if I state it in R3, these are all smooth. Okay, so you can manufacture smooth functions out of old ones as long as your target surface allows you to do it. Okay. And then, in terms of examples, of course, a large class of examples comes from this very simple observation. Suppose now that you have an old-fashioned function, smooth. So, O, remember, it's, for example, a ball of R3. Okay. And now, suppose that you are taking your surface inside O, or if it's not true, you take the intersection with this open set. Then, of course, you can restrict this function to S. Yeah, this is smooth. So the restriction of a differentiable function on the ambient space to a surface passing through this domain, is it still smooth or not? So now this goes from where to where? So this goes from S to R3, or to RK, or wherever you want. Okay. So where should I look? I'm in case 1. Okay. This is the situation I'm looking at. So is it true that for any chart? Well, yes. No, because the inclusion of S. Well, this is smooth. You check it online. So, well, of course, in particular, the inclusion, let's call it I, we will use it from time to time. If I take S is a subset of R3, so I can think of the identity map, which I call the inclusion, from S to R3, which just takes a point and gives me the same point. Okay? But now I'm looking at it as a map defined over S. So this is smooth. Why do I say in particular? Because this is the restriction of the identity from R3 to R3, which is of course a smooth map. And of course, what else? I mean, another trivial example, if you take as a function from a surface to RK a constant function, out of observation 3, you get immediately that it's smooth. So constants are smooth functions, of course. I mean, that's something, it has to be true, okay? Why? Because it's the restriction to a surface of the constant function defined over Rn, okay, over R3. Very good. Now, let's start defining few interesting differentiable functions. I mean, these are kind of the basic. I mean, on every surface you can play this game. But let's start giving names to some famous functions which will come up often. The height function Your height function is what? You pick a plane, actually now a picture would be useful. You take your surface S. Okay. You pick a plane, any plane, P. So P is a plane, S is a regular surface, I don't even write it, but P is a plane in a 3. That's fixed notation. I take one given, I pick one point, just as a reference point on this plane, P naught. And then, of course, a plane in R3 is given by what? I mean, which is the minimal amount of information you have to give me. One point and one vector, the normal vector. So let's give it a name. One normal vector. Okay, in particular, here in this situation, something like this. Okay. Okay, S is a regular surface, so now I define the function height, so I will call it H from S to R, which takes a point P and gives me what? So now I pick a point P here. Now P is in S. Right? Of course, the name suggests what we are looking at, the height. The height over this. What would you call the height of this point over this plane? Well, more or less the length of this vector, no? But the length with a sign, because the height could be positive, as in my picture, but could be also negative. You see, once you decide which normal vector have you taken, sometimes you have defined which is the positive part of R3 and which is the negative part of R3. Okay? So it's easy to write down. So it's the length of this vector, but with the sign, remembering whether it lies on the left or on the right of your plane. So you can write it. It's something like this. No, you take this vector and you project it orthogonal. I mean, you look at the orthogonal projection. Now this vector A, I can draw it wherever I want. Okay. So this is exactly what we have in mind, provided A is a vector of norm 1, because otherwise this is just multiplied by the norm of A. I mean, it's geometrically what it should, up to the norm of A. Okay? So, in this situation I don't have to correct it. I mean, I can take this function anyway, but I mean, just remember that this is exactly the height that you have in mind, only if A is a vector of norm 1. Okay? So the question is this a smooth function? Okay, that's all. But is it a smooth function or not?
Yes.
Why?
Because just the inner product would be the product of the components, and then we take sum, so it will be a linear function.
This seems a very good indication, but it's still not the proof.
Yes, it is a linear function of the coordinates of S. So if we have now a chart, and it will be a composition of this chart with this linear function.
Okay, now it's more elaborated. It's correct. I mean, in principle, I could write down this function around this point. I have to check whether it's smooth around P, and then I will argue that this is true for any P. So what your colleague is suggesting is, okay, imagine that you have a chart, because of definition 1, I need to take a chart, any chart, so one chart, and look at the composition. But the composition will look like smooth functions, because X, the chart, is made of smooth functions, and then scalar product with a fixed vector, minus P naught, of course, which is a constant vector, scalar product with a fixed vector, everything will be a linear combination of products of smooth functions. That's one way. But actually it's a little bit of a pity to make all this argument once we have made observation 3. Okay? if you look for the shortest proof, the point is this function here, why do we take it on S? This function is defined over R3, and it looks pretty smooth. No? Forget S, pick any point of R3 and compute this function there. Now I don't have the complication of the chart. I mean, I'm not saying it was a horribly complicated proof, but in this case, this is obviously, so this is smooth because the same function actually, h, but now defined over R3 to R, is smooth. So it's the restriction of a smooth function from R3 to S, to any S. Okay? Very good. So let's see another, so this is one important function. Distance squared. So now what does it mean? Now it means forget the plane. Let me not draw another picture. We pick a point P naught in R3. Now forget P, this is not part of my picture anymore. I have some point around R3, inside R3. And I take, how do I want to call it? No name. F from S to R to be just, now I pick a point P on S, and I look at what? The distance squared, of course, between P and P naught. Now, here I can write it in this way if I want. The distance squared is the length square of the segment P minus P naught. So again, is this smooth?
Yes.
For the same reason. It's observation 3. That's why I highlighted it, because it's useful many times. Because of course, forget S, as a function from R3, this is the sum of squares of the components of some given vector. Okay? So that's clearly smooth. And now, of course, just to complicate life, but it's clearly an important geometric function, the distance. Same thing.
But we need to, that B naught is not on the surface to make it smooth, right?
Sorry?
We need that B naught is not on the surface to make it
Now
smooth.
we get a condition. Now, if we don't square, and that's the distance, is this going to be smooth? In general, no, because again, it's the square root of something. Okay? So this is smooth if, I mean, how do I make sure that this square root doesn't create problems? Well, just assuming that P naught is not in S. But now, okay, now if you really want to write down a complete proof, you have to be careful, because wherever P naught is, it's in R3. So the same function defined over R3 will never be smooth. Now you cannot use observation 3 using O equal to R3.
You can take R3 minus the point B naught.
Now you take O is equal R3 okay, this is the open set you have to look at, okay, because this will never be smooth in R3. Okay, so we have at least three very, very important geometric functions: height, distance squared, distance. We will see how they enter into the game. And these are defined for any surface. Now, actually, there are a number of variables here, because there are points, planes, and so on. So, now, let me go back to the definition 1, because I jumped to examples and comments, but definition 1, if you think, it's very natural. It's still, basically, it's here. Definition 1 was here. How do I define F to be smooth? Well, I compose it with a chart, but this has to be true for every chart. So every time you try to prove that a function is differentiable with this trick, you enter hell. In fact, you enter, technically speaking, an impossible path. Because how do you argue that something is true for any chart, given the fact that there are infinitely many charts? In fact, even around any point. I mean, it's not just because there are many points on the surface. Around every point, there are infinitely many charts. So you need to find arguments which work for any chart. And that's a problem. You see? So it's very elegant, conceptually explains the heart of the fact, is that I want to transfer a property from S to R2, but then in practice it's a total disaster. Okay? Unless a little miracle happens. But actually it's not exactly a miracle. Again, the definition of a surface is designed to bypass this problem, to solve this problem in one shot. And this is worth a proposition. So, again, as regular surface, and suppose you are given f from S to wherever you want, Rk, now it's just a function. Now, if, notice the difference. Now what I'm going to write is, if around P there exists a chart, and this is, okay, around P. Around P means that P lies in X of U. Okay, so this is a chart covering P, such that F composed X so F composed X now goes from where to where? It goes from U to Rk. Okay. If there exists a chart such that this is smooth, then F is smooth. Okay, this is the little miracle. What is the difference between the definition? The definition is here. It's only here. Before, in the definition, you had for every. And now we pass to there exists one. Okay, this of course makes a huge difference. I mean, this means that in practice, this turns the definition of being smooth into a practical thing. Because now, around every point, I can manufacture my preferred chart and go and check whether something is true in that chart. And if it works, it works. If it doesn't work, it's game over. Okay? I'm not going to prove it. When I say this is an exercise for you, please try. It's an exercise for you. I really would like you to try. Otherwise, I mean, as you can see, I'm not particularly careful about giving you homeworks, but this is homework. I mean, this is homework. Exercise 1 in the sheet, in the first sheet of, okay? Now, of course, there is one arrow which is trivial. If it's smooth, this is true because it's the same sentence but for all. So, okay. So, of course, the point is to proving that if you have this property for one chart, you have this property for every chart. So, what is the idea? Pick two. I mean, you have this one, which is your favorite, your special one. Now, pick another one. Pick another chart. And you want to prove that the same property is true for the new chart. Okay? So the idea is, of course, to compose the two things with what is called the change of coordinates. Okay? And then you have to argue something. Very good. And this something is really important. Okay? So, okay, now we are done. We are done in the sense. We have a class of objects, regular surfaces. We have a class of transformations. In fact, everything here is important, not just maps between two surfaces, even maps from a surface to R, to R3, to R whatever, and so on. But in particular, we also have a class of transformations among surfaces. So of course, I don't even write it. If you have a smooth map between two surfaces, which are injective, bijective, with inverse smooth, then of course this will be your new equivalence relations in this new world. Okay? And you will call these things diffeomorphisms. So it's clearly more than homeomorphism, because I noticed that smooth implies continuous. Okay? So it's a new class of identifications among sets, which will work for regular surfaces. So eventually we will study surfaces up to diffeomorphism. Okay? Now we change subject, because remember, we are mimicking what we did for curves, and actually here we are still on the first page. We have the definition and few examples and maps. Now even maps between curves we didn't even define, because it was pretty obvious what they were. If you remember, actually after 10 minutes of curves, the first thing we said was, well, if I have a curve, for sure I have the velocity. I have a special vector associated to alpha, which is alpha prime. Well, now we have to suffer to decide what is the tangent space. Okay, that's the point. I mean, what is the tangent space to a surface? That's the new chapter. Well, in terms of sets, things are quite easy. So now we pick again, S is a regular surface, and P is a point in S. Because of course, now the aim is define the tangent space to S at P. So I have a given point, and I'm looking there. So we will call a given vector V over 3 is called a tangent vector to S at P if there exists a curve alpha defined on, I don't really care how small, but I mean a little interval at least. And now here comes the only delicacy with values in S. So of course epsilon will be some positive number that doesn't matter, such that alpha of 0. So passing through the point where we are working with velocity at time 0 at this point with velocity v. Okay. Of course, the set of tangent vectors to S at P, we give it a name, we will be denoted by TPS, and it's called the tangent space to S at P. Okay? So where's the only delicacy? It's here. Okay? So where is the restriction? Where is this? So what does every vector in R3, of course, is a tangent vector of a curve in R3. For example, the straight line. I take the straight line passing through P with direction V. So why does, claim every vector is a tangent vector to the surface? So what is forbidding this statement, which is of course stupid?
Not lying on that.
The point is that nobody is telling me that, for example, the straight line passing through that point with that direction lies in S. Okay? Very few surfaces will have, for example, this property. They will be extremely special. Okay, so requiring that this is the tangent vector of a curve whose image, whose trajectory lies on the surface. That's where the subtlety of the definition is. Okay? Now comes the crucial observation about the structure. I mean, this is as a set, but it is much more than a set. And the structure of this set is hidden in this lemma. That, again, with these notations, S regular surface and P a point, if UX is a chart around P, no? Now suppose that I take a chart around this point, then actually TPS, the tangent space to S, which is something, notice that I didn't use charts to define. This is kind of intrinsically defined. But in terms of a chart, I can write it as dx at the point x inverse of P over P. Okay. Okay. A picture is welcome again, even if it's always the same picture, but so I'm trying to understand what does it mean for a point, to imagine how should the tangent space at this point look. And this lemma is telling me, take a chart, look at where this point is coming from. This will come from some point here, x inverse of P. Okay. Now, the map X, remember, goes from U again to S, but why not? S is a subset of R3. Okay, so where does dx, so the differential of this map for any point of the domain, so for in this, I want to look at this, okay, at this special point, goes from where to where?
R2 to R3.
This is a domain of R2, so this goes from R2 to R3. Okay, and which property do we know about this map?
It's injective.
It's injective. So in particular, the image of R2 is what?
Two-dimensional.
It's a two-dimensional vector subspace of R3. Okay, it's a plane passing through the origin. Geometrically speaking, it's a plane through the origin in R3. Okay. So, of course, as I did for curves, remember that we always drew the tangent vector here. Now, vectors should be drawn with, always there. But to keep in mind geometrically what's going on, we will always draw the tangent space to the surface with the origin, the base point. But of course, that's a mistake in some sense. Okay, that's not, because that would not be a vector subspace of R3 if P is not the origin. Okay, but just to remember where. So otherwise, you have to think of this family of planes as P moves around. You have this family of planes through the origin in R3, which are moving, rotating around. Okay, very good. So you see why, in which sense, this gives me a nice structure to this set, because this is telling me this is telling me automatically that this is a two-dimensional vector space. Okay. Okay. Now let's prove it, because this is a deep result. Okay. So let's prove. Let's first prove this inclusion. It's an equality of sets, so let's prove both inclusions. Okay, let's pick a vector of R2. We have to argue that the vector of R2, the image through this map of this vector lies here. Okay. So where is it? So W in R2, and I'm thinking of W here, as kind of based here in my mind. R2, or Rn in general, is essentially the only place where I can play the following game. Actually, again, I should have drawn it here, but I drew it here just to remember. Basically, what this means, what I'm saying is that Rn is the only place where this magic happens. No? The tangent space to U is actually R2 itself. No? Rn, the tangent space to Rn is Rn itself. What does it really mean is this. If you give me a vector, of course I can take a curve that I want to call beta. Okay? So, for sure there exists beta of t. So beta goes from some minus epsilon epsilon in U, such that beta of 0, so this passes through the point x inverse of t. With velocity w. Here, you see, here I could even take the straight line, because this is a domain. Okay, I don't care, I don't want, but in principle, I could even take the straight line. For sure this exists. Okay. And now, of course, take this beta and throw it to the surface with a chart. Okay, I have a map x going there bijectively, so alpha of t will be by definition what? X of beta of t. So this, I define a curve on alpha, on S, on the surface. Why am I doing it? Remember the definition of a tangent vector, I just had to erase it. If I want to prove that something is a tangent vector, I need to produce a curve on the surface with this velocity, with the given velocity. So that's my candidate. Now I have, at least I'm sure that I have a curve on a surface. Let's see if it satisfies the properties it has to have. So what is alpha of 0? Well, alpha of 0 is x of beta of 0. Beta of 0 was this, so of course this is p. Good. So at least passes to the point p. And now, how much is alpha prime, which is its velocity? Well, or depending how you want to add. Whatever it is, its velocity vector lies in the tangent space to the surface. Because the tangent space to the surface is, by definition, the collection of all these objects. Okay? So on one hand, you know that this is a tangent vector to the surface. But what it is? Well, it's the derivative of this evaluated at time 0. But this, you see, it's my definition, is the generalized definition we discussed of the x of the tangent vector to that curve. That's why I spent few minutes reviewing what was the differential of a map. The differential of a map is by definition the derivative at time 0 of any curve, not just a straight line or whatever, of any curve passing through the point with this velocity, with the right velocity. Okay? So, on one hand I know that this has to be a tangent space, a tangent vector, and on the other hand, this is the image of the differential of the chart. So, I proved what I wanted. I proved that this object here, for any p and for any w, lies here. Okay? Well, actually, the opposite inclusion is essentially reversing all the argument. I'm not going to say anything. Because what do you have to do? Now, it's kind of the other way around. If I take v, and I know that this is a tangent vector to the surface at p, well, by definition, I know that there exists alpha, no? There exists alpha from minus epsilon epsilon into s, such that alpha of 0 is equal to p, and alpha prime of 0 is equal to v. This is the fact that v lies there, it means there exists an alpha. Okay, reverse everything I said. Now I have alpha here, I compose it with x inverse. And then I end up with a beta here. Okay? So now set beta to be x inverse of beta of t is x inverse of alpha of t. Okay? Now, this is a curve in U. So, what do you have to check? What is beta of 0? Beta of 0 is, again, it's x inverse of alpha of 0. This is, of course, x inverse of p. And then that's it. Because then whatever its velocity is, it will be a tangent vector to R2. It will be a vector in R2. Okay. So remember, we have to prove it lies here. So this, it's already here. Okay. Very good. So as I said, the main corollaries out of this are: 1, TPS is a vector space, has the structure of a vector space, which actually, it's highly non-trivial. I mean, think of geometrically of the definition. Actually, the definition of a tangent vector is written here now. Okay, V is a tangent vector if there exists a curve such that. Good. So what do you have, in principle, what did you have to prove? If you wanted to prove, if the exercise was, prove that it has the structure of a vector space. For example, pick two tangent vectors and argue that the sum, for example, is a tangent vector. Well, give me V1, V2. So if V1, there exists alpha 1. For V2, there exists alpha 2. And now you want to argue that for V1 plus V2, there exists beta. Good luck. No, because of course the obvious guess, I say, come on, it's alpha 1 plus alpha 2. I mean, if you want a curve in R3 passing through the right point with the tangent vector velocity, the sum, you take the sum. Yeah, that is the only problem, that the sum does not lie in the surface. I mean, it would be a miracle, an absolute miracle if it happens. Okay? So, it's actually game over. I mean, there is no way to bypass this problem. I mean, that's why you have to go to R2 with the chart, do it there. R2 is one of those miracles where you can play this game. So you play the game. So if you want to take the sum of two vectors, you go to R2. You do it there where it's trivial, and you send it back to the surface. You don't know exactly how, but X will do it for you. Okay? You have to appreciate a little bit the subtleties. I mean, because you say, come on, you want to prove this. What are we proving? That V1 plus V2 is there? Try. Try with the definition and you will fail. Okay? Then what? Also, in fact, we also have a canonical system of generators in some sense. So TPS, given the fact that TPS is the image of this thing, if I want the basis of this vector space, how can I produce it? Take a basis of R2 and you send it. Okay, linear algebra. Good. If I take a basis of R2 and we send it through the differential of the map, that's what we argued last time or 2 times ago. If you take the vector 1, 0 and you send it with dx, you get the vector take 0, 1, you get the vector. Remember the column vectors of we wrote the matrix representation of this with respect to the standard basis of R2 and R3. And it turned out that the column vectors were exactly the components of these two vectors here. So these two are the basis of the image. So just linear algebra rephrased. Okay? So every time I have a local chart, I have a standard basis of the tangent space. So these are tangent vectors and they generate. Okay? Now, are you with me? Questions? Because today's lecture is definitely, I mean, there's a jump in complication with respect to. That's why we spent time on curves doing simple things, because now everything is, it's the same, more complicated. The same, more complicated. I mean, you have to understand which is the analogy, but now every time it's more subtle. Okay? So if you have questions, don't worry. Ask, stop me. Now let's see in action on our class of examples of surfaces what this is giving us. Okay? In fact, the largest class of we have two very large class of examples, besides some specific like the torus of revolution or the sphere or the plane. I mean, this is something we can do by hand as a little exercise. But the two big class of examples we have are what? Graphs of functions and inverse image of regular values. Remember kind of this variation on the implicit function theorem. Okay? So let's see, for example, in this second case, what's going on. So suppose that we have, I recall you what is the picture in this situation. We have an open set over R3. We have a function, a real valued function, f, defined over R. So this of course is smooth. I mean, if I write a function and I don't say anything, it's assumed to be smooth. And A is a regular value for f, which I recall you means that for any point on the level set, the differential is non-zero. Okay. And of course, remember the triviality. I also want the level set to be non-empty. Okay, because otherwise, in principle, if it's empty, it's a regular value. So, but that's the triviality I want to avoid. So in this situation, remember what we argued was that f inverse of A is a regular surface. Of course, here I'm assuming that this is non-empty to avoid stupidity. Now, in this situation, how does the tangent space look like? That's the new object we have. So claim. It's actually something I'm sure you have seen it written in different ways many times, because level sets arise in many branches of mathematics. So I'm sure you have computed already the tangent space to the level set of something, but probably not in this generality. Okay, so I claim that actually the tangent space is the kernel of the differential. So the differential of the map will go from where to where? From R3 to R. Okay? And it's assumed to be non-zero because it's a regular value. So how big is the kernel? 3 minus 1. Okay? So at least it has the right dimension. This doesn't prove the claim, of course. At least this object, it's a claim about two-dimensional vector spaces. Okay? Have you seen it? You knew it? Written in this form? I'm sure you knew it in another way. We will come to that later. Because this is a plane, written in this form, maybe you didn't, but this is a plane, so it's a plane in R3. So actually it's given by, it has to be a vector space, so remember, a plane is given by a point and a vector. The point, it's a vector space, the point is the origin. So it's given just by a vector. Do you remember? I'm sure you have seen many times. What is the normal vector to a level set?
Ah, the radius.
Which is the direction in which the function has the steepest change, because that's what it really means to be. Okay. And that's more or less what's written here. In any case, let's prove one. Again, this is an equality of sets, so we have to prove two inclusions. Let's prove first this. So I really take a tangent vector, and I want to prove what? I want to prove that the differential of f at p evaluated on this vector v is 0. I'm claiming that this annihilates this function. Okay? I just write down the definition. If this is a tangent vector, there exists alpha, I could import that line. Okay, definition. So I have this curve on the surface, which integrates this vector here. Very good. So how much is f of alpha of t? Alpha of t lies in S, and S is the inverse image of A. So f of alpha of t, f of S actually, of every point in S, has to be A. This is the inverse image. So in particular for the points of this curve. So this is equal to A for any t. Take the derivative. Okay. Of course, if I take the derivative, I get what? On the right, 0. And on the left, the differential, by definition, the differential of f at p of the tangent vector to the curve. And that's exactly what I want. Okay? So this is not the v. This is end of proof. End of proof of this inclusion. Now I should prove the opposite inclusion. But do I? It's always good to think before wasting 5 minutes. No. That would be a waste of time. Because I know already that these are two-dimensional vector spaces. One is contained in the other, then they are equal. See, the only thing that could go wrong in the other inclusion, of course, is that this is bigger. I already proved that this is inside here. How can, this is a vector space, it's a subspace over 3, contains a two-dimensional vector space. The only way this could be bigger, it could be the whole over 3. But that would mean that the F is the 0 map. If the kernel is R3, this is the 0 map. But this is forbidden. So there's nothing to prove. Okay? So linear algebra saved 5 minutes of our life. And you see, now you can apply, for example, this idea. So now remember, this is a magic formula. This is very helpful, I mean, at least in various reformulations, but this is very helpful many times. So let me erase the proof. So let's see it again in action. So this would be kind of a sub-example 1, because, for example, certainly the most famous regular value that we know, but I mean, probably the most famous regular value in general, is to write down the sphere as the inverse image of something, no? So let's compute the tangent space to S2. Actually, I think now we can be, so the two sphere of center P0 and radius R. Okay? I mean, why this falls into this category? Because S2 P0 R is what? Is F inverse of R squared, where F of P is which function? Now defined over the whole of R3. Well, of course, the sphere is the set of points with distance squared from a given one, r squared, okay? We have already argued that if r is non-zero, this is a regular value, so we know. But then what is this saying? What is the tangent space to the sphere? So it means we have to compute the differential, I mean the kernel of the differential. So in particular, I don't remember if I computed already. When we argued that r squared was a regular value, of course we computed the differential because we had to argue that this was non-zero. But in any case, it takes a second. So what is dfp v? In fact, you have to learn to do it while you write. This is the derivative at time zero of f composed, a curve passing through p with velocity v. I mean, let's redo it, but where alpha, I don't even write, where alpha is a curve such that alpha of 0 is equal to p and alpha prime of 0 is equal to v. Okay? Then I replace f with its expression. This expression, of course, now it's convenient to think of this as the scalar product with itself, because I'm quicker in doing derivatives. Now p has become alpha of t. So if I take the derivative of alpha of t minus p naught, alpha of t minus p naught, of course the scalar product gets differentiated like the usual product. So this becomes derivative of the first, which is alpha prime, evaluated at 0, which is v. So now, maybe a little bit of space. It's alpha v. Then of course p naught here has disappeared because I'm taking the derivative. But times the second, so this is alpha of t at 0. So here it survives. Plus this one, derivative of the second, but it's the same thing reversed. So, okay? Very good. And now the question is, what is the kernel of this? I think it's actually
Things that orthogonal to
that's probably the first theorem we studied in high school in three-dimensional Euclidean geometry.
just the things orthogonal to this.
So what is the tangent space to the sphere at a given point? At the point P, the tangent space, so this object here is equal to the set of vectors. It's written here, I'm just copying, so it's just the set of vectors for which this is 0. I mean, if the scalar product is 0, it means they are orthogonal. So it's actually, it's the orthogonal to the point itself. So the normal vector to the tangent space is actually the point where you are computing the tangent space. I always found it beautiful. I mean, I don't know why, huh? I mean, this is just pure psychology, but sometimes I remember when I was in high school, I say, come on, this is, of course, this you can also try, if you like it as I did it, you can prove that that's the only surface which has this property, of course. Okay. It's one way to say what is a sphere. So, now, okay, I'll stop here in terms of examples. Actually, maybe in the homework I will ask you to compute the tangent space to the graphs, our second class of, big class of examples, okay? That's easier. I tend to do the most difficult things in class. Okay. Now, next conceptual step. We have surfaces. We have transformations among surfaces. We have the tangent space to a surface. Now it's time to define, given a function between two surfaces, the differential of the function. Okay? It's clearly a very important object in calculus, and at the end of the day, what we really want to do is calculus, but not in Euclidean space, but on a curved space. So we need a notion of differential of a function, now defined over a surface. In fact, let's give it a name to this chapter. Okay, so that's what we want to gain now. Let's start with a function from a regular surface, again, with values in Rk. Then eventually we would like to have a notion for maps between two surfaces. But let's first see if we just restrict the domain. So this is, of course, it has to be smooth, otherwise we cannot proceed. And the differential will depend on the choice of a point on the domain. So let's fix p-ness. Okay. Now, we have an obvious guess, which is take the old formula and rewrite it. In fact, it looks like I'm cheating. So I take V in TPS and I define the differential of this map at the point P applied to this vector V. So remember, which was the formula, the one I used without even here? It's d dt at t equal to 0 of f composed alpha of t, of course, where alpha is a curve, which I know it exists because v is a tangent vector. So where alpha from minus epsilon into s, okay, is alpha of 0 is equal to p and alpha prime of 0 is equal to v. Okay? Very good. Why not? This was the differential for maps from Rn to Rk. Let's take it. But again, there is a little problem. What do we need to prove? That this does not depend on alpha. Given any v, there are possibly infinitely many alpha with these two properties. Actually, with these three properties now. Okay? So I need to be sure that this definition does not depend on alpha. Remember, when I write this thing, it doesn't mean it does not depend on any alpha, up to this, otherwise. Okay? And actually, the idea to prove it is exactly what we did. Remember when I argued the same thing for the classical differential, which was the proof? I said, I don't prove it. Actually, that didn't seem like I was going to prove this. I wrote it down. Okay, I wrote it down and I computed the matrix representation with respect to standard basis, and I noticed that magically alpha disappeared. Good, let's do it. Okay? But now, if I want to play that game, I need to take a chart around P. Okay? So, XU chart around P. And this is good actually, because I remember that playing that game, even in the classical case, gave me more than just this statement. Gave me also a way to write it down. So it was well spent time. In which situations are we? We have this curve. Now, of course, assume alpha of the whole interval, the image of alpha. Suppose I have taken epsilon sufficiently small such that alpha of the interval is contained in x of u. I can always do it because U is an open set containing P, chart around P, so alpha must be contained in an open set if epsilon is sufficiently small. Okay? Very good. So what do? I take this alpha, which lies on the surface, and I pull it back to R2 with X inverse. No? Set, I think I usually call it beta. I don't give it a name. So look at X inverse composed alpha. Now this satisfies what? So X inverse composed alpha at time 0, well, it's X inverse of alpha of 0. Alpha of 0 is P by assumption, so this is something. It's just X inverse of P. Okay? And now I just take the most stupid equation I know. I mean, the only thing I know really is that X inverse composed alpha, I just put brackets, and this is equal to alpha. You remember, the only thing I know is that alpha prime of 0 is equal to V. Okay? While I want to compare the tangent vector to alpha with the differential of this map here. So I play this game. If I look at this equation and differentiate in T, what do I get? Well, on the left, and of course, and evaluate at T equal to 0. What do I get? Well, here I take the derivative of alpha, derivative in T equal to 0. I get V. Okay? So how do I write this monster here? Because now I take the derivative of T at T equal to 0 of this object here. Don't be worried, don't be scared, because, okay, it looks like many symbols going around, but this is x of a curve, and I'm taking the derivative at T equal to 0. So this is by definition dx at the point x minus 1 of P of which vector? Well, of something. Actually, there is no better way at the moment to write it as just like this. Of this vector. Okay? But now, on this, I mean, this was all about how to translate vectors and curves from one place to another, from S to the chart. What we're really looking at is a map and the differential of the map. So now I have to compose F with alpha and see what's happening. On the other hand, what is F composed alpha prime at 0? Because that's what is asking the definition. Well, here again, I play if I want to put this object into the game, the only thing to do is this stupid F composed, it's d in dt t equal to 0 of F composed X composed X inverse composed alpha. Okay? Doesn't change anything, of course. And now, again, don't be scared. What is this? Well, this is the differential of this map evaluated at the point X inverse of alpha of 0. So maybe I should have given it a name. X minus 1 of P. Of which vector? Of X prime composed alpha prime at 0. Oh, it's better to exaggerate with brackets. Okay, this is just by general theory. But now, okay, the first part is okay, I cannot do anything better than that. This is F composed X x inverse of p. But now I learned something here. So now I have this strange vector there, x inverse composed alpha prime at 0. Where do I get it? Well, I get it from here. Remember that dx is invertible on the image. I mean, dx is a map from R2 to R3, so strictly speaking, is not invertible, but it's invertible on the image because we know it has rank 2. So with this caveat, I'm going to write the inverse. So I can apply the inverse to both, because I'm allowed to do that because I know I'm in the range where it exists. Okay? So this object here, I'm going to write it as dx inverse of v. Okay? Which means what? Well, now I can just rewrite it. So what have we really proved? This object here was this one. Okay, so in fact this was dfp. Now I dropped the v. So as maps, this map, I wrote the differential of the function as this, this beautiful thing. As maps, no? Because now every time I prove that every time I plug v, I get the same thing. Okay. And now this proves exactly what I want. Exactly the same philosophy. The magic happened again. This was written in terms of alpha, and actually that's the way you compute it actually in reality, in real life. You pick an alpha and you take this. But you need to know, the theory must tell you that what you do is independent of alpha. Okay? And this is the proof, because on the right there is written something horrible. I don't care if it's horrible. Alpha disappeared. Okay? So once we have, so this explains why the definition is well posed. Okay, we have a well-defined thing. Now, of course, really what we really wanted was to be in this situation, no? I mean, this takes care of the domain, but what about the target? Well, the point is that the target here, it's irrelevant, because again, I forget it, this is an R3, and I use this. Only one observation. If you are in this situation, so here you would say what? The df, let's go back in this part of the blackbird. Okay? So this proves it's well defined, but where does it start and where does it go? So dfp goes from where to where? Takes a tangent vector to the surface at the point P. So the domain is TPS and goes where? No idea. Gives me a vector of R3. That's the only thing I know here on this blackbird. So in fact now let's call it capital F, because otherwise we get confused. Okay, so this is for this type, of RK. Okay? If I'm in this situation, if I want to compute the differential of F at a given point P, I take the same formula, forgetting that S1 is actually inside R3. Okay? So, if I apply the general machinery, what should I tell you? This goes from TPS to R3. Can I say something a bit more?
Yeah, it is injective, so at most the image is two-dimensional, therefore I can identify it with the tangent space of S1, because the tangent space of f of b, the tangent space of S1 at f capital B is two-dimensional, and the image is also two-dimensional vector space, so I can identify them.
Your guess is right, you are almost there. You are arguing actually something which is not true. This two-dimensional argument you are giving seems like this differential has to be surjective. It doesn't matter. It does not have to be surjective.
I didn't say it's surjective. I'm just saying that the image will be two-dimensional.
No, that's what I'm saying. How do you know?
At most two-dimensional, because it is injective.
You don't care. In fact, suppose actually it's a constant map. This map is zero. The differential of the constant has to be zero, otherwise everything is wrong.
But the image is at most two-dimensional.
It's at most two-dimensional, but you don't, it could be whatever. What I'm saying is this part of the, you're right. I mean, you made the right guess. It's actually here. But to argue this, you don't need to argue, you just look at the definition. Okay? F of alpha, I mean, given alpha here, f of alpha is a curve on S1, and you are computing its tangent vector at time 0, passing through the point f of p. So whatever I get is not any vector of R3. It's for sure a vector in this two-dimensional subspace. Without arguing how big it is, whatever. Okay? So that's the only difference between having a map between a surface and Rk and between two surfaces. I mean, you know a little bit more about where the target, which is the target of the map, of the differential. Okay, so then, of course, you start doing calculus. So typically, one of the most boring things we all had to do in calculus was to do what? Prove chain rule. No, that was really horrible. You still remember. But now, so now, what does it mean, chain rule? I mean, and you really have to prove it, because suppose you are in this situation here. Then, of course, the obvious question is, what is the differential of the composition in terms of the differential of the single components? Fortunately, we don't have to prove it. Because given the definition, given this horrible formula, there is a formula that tells me that this is actually a composition of the old differential. It's the old differential composed with x, dx, blah, blah, blah. Fantastic. That's, we don't have to take back our book of calculus to prove this one, because this the old theorem will imply the new theorem without doing any computation. I mean, given the chain rule for maps from Rk to Rm to Rl to R, you get automatically the chain rule for maps between surfaces. Okay, just by composing with charts again. Okay? And that's, of course, very useful. And let's finish. Let's finish with one geometric application of the differential, because otherwise it seems like we are just mimicking calculus. Even just the fact that we are able to compute the differential is already interesting to deduce some nice geometric properties of something. For example, let's take one of the famous functions we defined at the beginning of the lecture. So let's take the distance squared. So example, f, so remember, S, we have S, P naught in R3, and the function f was defined from, well, actually, from S to R, and was taking P into the distance squared from this point P naught. Okay, so this is, let's look, for example, at this function here. Okay, let's compute the differential. I mean, this is supposed to be an exercise on the differential, but actually I hope you are getting bored and a little bit offended. I mean, how do you compute it? Without even writing, okay? Now, for this time it's here, so you imagine that you are taking a curve, alpha, on S, with alpha of 0 equal to P, and alpha prime of 0 equal to V. You compose it, and you take the derivative. This is again the square, no? Actually, it's what we computed for the sphere 10 minutes ago. Okay? So this becomes twice V P minus P naught. Same computation actually we did before. And actually this goes from where to where? So the FP goes from the tangent space to the surface into R. Okay? Now, this would be kind of the exercise for the differential, but actually this formula is hiding something interesting. Not just in the case of the sphere. So, you see, every time you see a function, almost immediately, without thinking, you are asking yourself, does this function has a minimum, a maximum, a critical point? I mean, somehow we are thinking of this type of problems all the times, no? Min, max, critical points, and so on. So let's see. Is it possible for P to be a critical point? Critical point means the derivative is 0. Now, the derivative now is a map. So, but a map, the differential, it's 0 if it's the 0 map. So how is it possible that dfp of v is equal to 0 for any v?
If B naught is in the surface itself.
Sorry?
No,
Let's see. Well, it's a little bit like before for the case of the sphere. It's just the fact that now we don't know that S is the inverse image of a regular value or whatever. But I mean, of course, this means what? This happens if and only if
V equals V naught.
V. So now, before we knew the sphere, we knew the surface, and we were looking for the tangent space. Now, in some sense, we are doing the opposite. No. So V has to be orthogonal to P minus P naught. Okay? Now, geometrically speaking, I can rephrase this geometrically by saying, so this is actually, this has to be true. This is what I was missing, the most important part of the sentence. The FPV equal to 0 if and only if V is orthogonal for any V in the tangent space, because this has to annihilate the whole tangent space. Okay? So, can you imagine a little bit geometrically what's going on? I mean, you have your surface, you have a point, and you are measuring the distance squared from this point. Now, here, so question, could this P be a critical point for this function? Well, I imagine I know the tangent space at this point, and so what this is saying is that any vector here, now unfortunately I drew a very bad picture because this looks like a sphere. I mean, on a sphere, of course, every point is a critical point. So if you want to draw a meaningful picture, you have to draw something very different from the sphere. So suppose actually your surface is something like this. Okay? And here you have your point P, P naught. Okay? So could this point here be a critical point? Well, this would mean that the tangent space is orthogonal to P minus P naught. And this is clearly not true, for example, in this at this point of this picture. Okay? So geometrically, how do I phrase it? I can phrase it by saying if and only if P minus P naught is the normal vector to the tangent space. I mean, the tangent space, after all, is a two-dimensional vector space. So if and only if P minus P naught is the normal to TPS. Or, another elegant way to say it, if and only if the normal line to S at P, so what is it? Of course, the normal line goes without saying. I mean, I have a two-dimensional vector space, I have a normal vector, I take the line with this direction passing through the point P, okay? So the normal line to S at P passes through P naught. That's something I can really see. Give me a picture. So I can really see, looking at the picture, without doing any computation, whether a point, at least it's plausible. Then of course I always have to make computations. But I mean, if it's plausible that a point is a critical point for this function. Okay? I guess in my picture there is only one reasonable candidate, no? It should be somewhere here there is a point which should be, because if I imagine the normal line at this point, it really looks like more, it's going very close there. So, there is only one problem, is that in general a function might not have critical points. That's a pity, no? There is no theorem which tells you that if you take a function over a domain, it has a minimum and a maximum, for example. But a little bit of topology helps. So, for example, how do I make sure that some critical points exist? For example, if S is compact, any real valued continuous function must have a maximum and a minimum. And now, okay, I never checked the old theorem in calculus, but I mean it's obvious. If you take a maximum or a minimum, this is a critical point in this generalized sense. Okay, if S is compact, there exists at least two. Well, if F is non-constant. Because if it's constant, it's everything. Okay, at least two except trivialities, okay? Critical points. Okay? I'm saying that at least the minimum and the maximum exist of this function. So, if S is compact, if you take a compact surface, I can, well, in fact I could even rephrase it. So now suppose it's compact. So now it's just a game of, you can rephrase all these things which is written on this blackboard, you can rephrase it as you like. Let's play this game, for example, in this way. I pick S. Now, if S is compact, there are two critical points of any function f for any choice of P naught. So remember, f depends on the choice of a point. But however I choose P naught, there are two critical points. Okay? Now, so, and having a critical point means this. Oh, that's a bit funny, no? That's saying if you take a compact surface, through every point of R3, there are two normal lines of any surface passing through this point. It's a bit curious, no? I mean, the question could have been, a geometric question could have been, now you know what is a surface, now you know what is the tangent space. For every point, now you take a compact surface. You take a compact surface in R3, you imagine that, play this game, at every point you draw the tangent space, For that tangent space, you draw the normal line. Now think of this mess. This is kind of a spaghetti craziness in R3. You are putting a spaghetto everywhere. Okay, normal to this. Are you covering R3? I mean, for every point of R3, is there a line of this type passing through this point or not? I mean, that was a very legitimate, interesting question. The answer is actually yes. If the surface is compact, for every point of R3, there are in fact at least two of these lines passing through this point. Of course, the same as if you drop this is clearly completely false. Think of S to be a plane. For every point you draw the tangent space and you take the normal line. Oh, sorry. In this case, of course, every point of R3 is hit by one normal line. So how do I imagine a situation where this is not true? We can think of it. I mean, now we are already over time, so let's not waste time. Okay. Okay, now I think it's over. I mean, we can keep on reformulating. I mean, you can play also another game. Now, suppose that instead you have a geometric assumption, like there exists a point such that for every normal line passes through this point. So suppose you play the opposite game. You put a condition on the fact that you know where these normal lines pass. And suppose, for example, there is a point where every normal line passes through this point. Can you deduce anything? Because that will mean, suppose that you know that actually this function, every point is a critical point for this function. No? If the normal line passes through this point, it's a critical point. So now I'm kind of assuming. Suppose that every point is a critical point, said geometrically. But if every point is a critical point, the only possibility, if this is true for any p, the only possibility is that f is a constant. But if f is a constant, f is this one. So which surface is it?
Sphere.
It's the sphere. Okay, so that's a characterization of the sphere. That's what I told you before. That's how you prove it, that the sphere is the only surface for which this little miracle works. Okay? Well, of course, if S is also connected, because if it has more than one connected component, then it's a bunch of spheres. You know what I mean? Okay. This was kind of for free out of the definition of the differential of a group.